looking at the MPG, again, I can see that there are a lot of outliers. Now, if I want to do some regression on this, I don't want a lot of outliers that will skew my model, right? So I'm going to remove them. And I just made a small function that said that if any MPG was less than the combination of the median plus the standard deviation, then get rid of it, right? And about 3,000 data points were lost, which is no big deal. And when I plot it again, you can see that there are not many outliers, but also you can see that there's quite a large overlap between German vehicles and Japanese vehicles, and this will play a part later on, right, when we try to model where a vehicle comes from. So I'm going to basically breeze through this area because we don't want to spend too long on it. Again, just some pretty pictures looking at the relationships between some of the features. As you can see, cars lower on the engine displacement generally have lower fuel costs. Cars higher, there's a positive rise in relationship between the annual fuel cost and the engine displacement, and there's a negative correlation between the combined MPG and engine displacement. Okay, so a good thing to do to look at the correlations between every single numerical value is to do a pair plot. So a pair plot basically gives you an overview of the behaviors between each features. The diagonal just shows you the diagonal shows you the distribution of each features, and as you can see here, pretty much all the features look sort of bell curvy, right? They look sort of bell curvish. And this plays into the decision I make for how to scale my features. I eventually use a standard scaler because it's just a simple scaler to use, and it works very well on data which takes the shape of a bell curve. Okay, so this is where I transform my data. So step number 6, I need to prepare the data for my machine learning models. And using the sklearn library, this is the standard or the most common machine learning library or in Python. Another one is TensorFlow, and there's another one which I don't know, can't remember the name of, but the one I use most often is sklearn, simply because that was the first one that I learned, so I'm just used to it. I make some slices of categorical features and numerical features. I need to standardize the numerical features, and I need to encode the categorical features, and that basically forms my transformation part of the pipeline, right? So pipelines are basically interconnected steps or stages that are designed to automate a certain protocol. In this case, my machine learning or my data analysis into machine learning protocol. So if I was to actually do a proper pipeline, then this encoding scaling stage would form 2 nodes in my pipeline. I don't think I used pipeline eventually because this example was just to show a very easy to follow tutorial of some data analysis and machine learning, so I didn't want to make it too complicated by adding in pipelines as well. Again, I make 2 functions, one to encode the categorical features, and the second function to scale the numerical features. Okay, because I don't want to have to manually scale the data and then have to do numpy arrays and then pandas data frame to turn it back into a data frame and add it back to the data frame. I just used this column transformer script to basically automate it for me, right? So I can scale the data and have it back into my original data frame, okay, with the appropriate column names, right? So that's what that has done here, and as you can see, my data is scaled, and I believe I have transformed I've encoded the columns too. It should be here somewhere. Yeah, there it is. So I've applied the standard encoding function on my categorical features and basically updated the columns according to their categories. So now we are ready to look at the correlation matrix once more. And if we note here, just looking at combined MPG, once again, there's strong and negative correlations with engine cylinders and engine displacement. And there is a strong negative correlation with annual fuel cost, and there's a strong negative correlation with tailpipe CO2. Now, really and truly, you're not really supposed to model your target. So our combined MPG is our target, whereas the rest of our features are our features. You're not meant to model every single feature, but I did it anyway because I was being lazy. But you're not meant to do that. You're meant to take only the features that matter the most. So now we do modeling, and this, by and large, is the easiest part of data analysis, right? So when you look at a machine learning tutorial, for some reason, most of the tutorials that I've ever looked at don't talk about train test split until several chapters down the line, which I do not understand. A lot of machine learning tutorials actually train and model on their training set, which I disagree with. I still model on the training set, but only to see how good my model is, and then use that same model to test on the test set, or to fit to the test set. So this is called train test split, is a version of holdout. So you split your data into two sections, right? You keep most of the data for training. This is where you basically train your model and make it smart, right? And then if you're happy with your model, you then use it to predict your test set. And the closer your model aligns with your test set, then the better your model is, usually. Occasionally, overfitting crops up, and overfitting is an issue. You don't want to overfit your data, but neither do you want to underfit it. So what I've done here is that I've used the train test split to split my data into 80% training and 20% test. I'm going to train my model on 80% of the data. Then once I'm happy with my model, I'll use it to predict the test data, and then I'll use root mean squared. Root mean squared error to see how far they differentiate. Okay. So it's a common joke, right, that when people learn about machine learning for the first time, they use nothing but linear regression. So linear regression is the easiest type of modeling. You're just modeling a straight line, right? Straight line with coefficients. And linear regression is not the best thing to use. I'm going to use it anyway, just to, because it's everyone's first model. If you've ever, often the first data set that you will use for machine learning is either the Boston housing data set or the California housing data set. And we use linear regression for that because the median price of a house scales linearly with a lot of features. So the reason why linear regression is bad, because if we look at the pair plot, we can see that MPG it's not very linear, right? There's some linearity here, but it's very, very noisy. There's a bit of linearity here, but there's curvature. And here, I'm not sure what's going on there. So I can predict that the linear regression model isn't going to fit the best, but we do it anyway. So as you can see here, I fit my lin model, so I call linear regression, and I fit it to my training set. And then I use my model to predict the training set to see how close the model works, right? And then using NumPy, I do the square root of the mean squared error, and I get 0.72. The lower this number, the better. Okay. And then another way to basically try to improve your RMSE score is to cross-validate, right? So that's basically splitting the data into a bunch of folds and then training on those folds. those folds don't talk to each other, so there's no chance for the model to basically prematurely learn from itself. So this is a way to basically try and get a better score. Not much improvement there. So let's predict on the test set, and we see that it's 0.7, and the data is reasonably okay. But as we can see, there's curvature. So this means that the model doesn't perfectly predict the actual values for the miles per gallon of a car based upon the features that you feed it. So if we were to take this model, right, and apply it to a fresh data set with the same features, so annual fuel cost, fuel type, engine displacement, it would do a decent job of telling you, hey, this BMW would have a miles per gallon of this. Do you want to buy? So that could be the decision making. If the MPG is too high, oh, you shouldn't buy that. If you want a car, sorry, if the MPG is too low, you shouldn't buy that. If you want a car maybe above 20 MPG. So this is what a machine learning model will help you do to help you make decisions. Okay, so this isn't that great. So what we can do is that we can use a better model. I personally used support vector regression. So I used support vectors. I used a support vector model because my data has a lot of features, and support vectors are very good at predicting data with some non-linearity, right? So I chose support vector with a polyfit because I know that it's not going to be a perfect linear fit. So the same kind of principle here with the linear regression, where I'm using the same train test split, and I'm fitting with the training data, looking at the RMSE on the training data, and then is it good, bad, whatever, and then using the model to predict the test data. And as you can see, we get a lower value, so 0.52, which is good. It's better, but I think it could be better. So I decided to look at the parameters of SVR. I'm not going to go too much into this, but these are basically parameters that you can use to modify your model to fit your data better. Okay, and I basically do a random search, choose these pairings of parameters, or choose this assortment of parameters, and give me the best one that fits the data the best effectively. So I basically done that, and I've chosen this code. I've chosen the best estimator using this line here, and using that estimator I fitted the data again, and as you can see here, I get an RMSE of 0.2, and when I draw the plot I get an almost perfect straight line. Now the reason why there are values here is because MPG is actually categorical, or it's behaving like a categorical value here, but this is basically what we want. Okay, we want almost perfect predictions. Okay, so that's good so far. So to tie this off, I want to predict where a car comes from with using its features. So going to pair plot again, and this time changing the hue to country. So I want to see how the distributions are differentiated by country, and I just want to look down the middle. I want to look down the middle because I want to see how the countries differentiate each other in drive, engine cylinders, and all these other features. With the exception of make, we can see that pretty much all of the features are overlapping. It's going to be difficult, with the exception of engine displacement. When I first did this, I actually dropped engine displacement because I made the wrong assumption that engine displacement had the same information as engine cylinders. And the model was just awful at trying to predict a Japanese car. But there's a sliver where there is some differentiating between a Japanese car, an American car, and a German one. So I put engine displacement back in. Now I'm going to use an ensemble here, right? Now an ensemble is an amalgamation of individual models. And the whole reason why you would use an ensemble is to give a better prediction. Now I use two different types of ensemble, right? The first ensemble that I used was a voting classifier, whereby I used three different models and then I aggregated their scores. Right? So I used a logistic regression, a support vector classifier, and a decision tree classifier. I trained the data on each and every single one of those models to get my accuracy score, so how well the model predicted, and then I aggregated those scores. Right? So after all said and done, this particular ensemble can predict an American car and a German car with 91% precision, but it is very poor at predicting a Japanese car. So we need to do something about that. We need to improve our model, right? So the ensemble cannot predict Japanese cars well. So I'm going to try another ensemble, which is called a stacking classifier. And what a stacking classifier does is that it has some base models, and then the outputs of those base models are used as the input into the final model, right? So the base estimator, I used a random forest and a support vector classifier, right? And then the outputs of these models are going to be the input into a logistic regression estimator, right? So in a sense, this stacking classifier is learning from itself. It's learning how to make better decisions by looking at previous models. And as you can see here, the accuracy is very, very high now, much higher than what it was before. So here we had an accuracy of like in the 70s, low 90s. Now we have accuracies all across the board, like low 90s, and that's fair enough. We make the final ensemble and we see that we can predict an American car with 93% precision, a German car with 96% precision, but best of all, a Japanese car with 76% precision. So we've massively improved our ability to predict whether a car comes from Japan based upon its features. And just to prove my point, I'm showing the scaled values of engine displacement, and as you can see here, there's a lot more to differentiate between the different vehicles. Remember before, there wasn't too much to differentiate between the countries I meant to say. Here, there's a lot of overlap here. There's a lot of overlap with the exception of engine displacement. So it was important that we kept engine displacement in there. So hopefully this video was not too long. If it is, I'll probably just cut it in half and upload them as part 1 and part 2. Thank you very much for watching. Should anyone want to look at the code in a bit more detail, I'll upload it to a GitHub, which you can access and have a look at it yourself and use it as inspiration to any personal machine learning projects you may want to undertake. Thank you very much for watching. I hope you learned a lot, and I'll see you in the next video.